Hello. Like me, your calc teacher told you that FRQ number 6 is probably not definitely, but like 90% going to be a serious question, and we did Taylor series like a month ago. Look how small it is in the distance, like cute little guy. So let's quickly go over how these work for both of our sakes. Now, I'm guessing that you know the series are the sum of a bunch of terms called a sequence, and we could write this series like this, or more generally, any series like this, where k is where we start from, and the number on the top is where we stop. But since infinity is on top, which is not a number, we're trying to add infinitely many terms, which might be a little hard to understand. That's okay, I still love you. A Taylor series is like we're trying to get really, really close to some function that we can't calculate with that table or calculator, and we're only allowed to use polynomials because those are actually possible to calculate by hand at any real x. You couldn't tell me off the top of your head what sine of 1 is. There's some kind of math wizardry here, but if you want to think about it, it's like you have to match what the function is right there, then slope right there, then the concavity, and then the rate at which concavity changes, and then you have to keep going down and down forever with all the slopes of the slopes until eventually you made a really, really long polynomial that perfectly matches up with a real function. And this is what your average Taylor series looks like. You might get a question about a Taylor series that doesn't follow this, in which case you fall back on the rest of your series knowledge, but this is what most Taylor series look like. If you do happen to get a Taylor series that doesn't look like this, remember the whole sum equals the function as long as the term of the sum eventually equals 0. The C around is where we're estimating, since if you do only a little bit of the Taylor series, then it would be a really bad estimate if I was doing everything around x equals 0, and then tried looking all the way over here at x equals 5. The n in f to the n of c is to represent the nth prime, since it's really hard to write infinite or unspecified apostrophes, and n in general is just how many terms deep into the Taylor series we are, minus 1, since we start counting n from 0. The exclamation mark is the factorial symbol. You can read these as 3 factorial and n factorial. And that means to multiply that number with every other number below it until we get to 1. So for example, 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And 5 factorial is 5 times 4 times 3 times 2 times 1. We can shorten the sequence down to this series. The sum from n equals 0 to infinity of f to the nth prime of c times the quantity of x minus c, that quantity of power, all divided by n factorial. This comes in if we're doing the partial sum of a Taylor series, which is if we're not adding infinite terms, we stop at some number of terms in. If we're only doing the first few terms, the partial sum of a Taylor series is just a pretty decent estimate around c instead of being a perfect replica. With that out of the way, let's say we don't have infinite time and we don't want to add up infinitely many terms, and I say, okay, estimate e to the x around x equals 1 with the first 4 non-zero terms. Hold on to the non-zero terms part for later. Let's start filling out the partial sum of the Taylor series of e to the x. Let me go through the first terms step by step by using the general term before we skip ahead and just use the Taylor formula. For our formula, let f of x equal to e to the x. Our first term is where n equals 0. The 0th prime of f is just plain f, since we're centered around x equals 1, c equals 1. We plug this in, and we see that f of 1 is equal to e to the first, which is equal to e. X minus 1 to the 0th is equal to 1 due to any number to the 0th power equaling 1. 0 factorial is equal to 1 due to math magic, so the first term is just e times 1 divided by 1, which is equal to e. You do this again for all the other terms you need, but that's pretty long. If we use the regular formula, then we can get to the same place a lot faster by just plugging in the values it's asking for all the way out to however many terms we need. If c is equal to 1 and f of x is equal to e to the x, and all derivatives of e to the x equal to e to the x, then all it takes is a little bit of substitution, and it's all done. Therefore, the partial sum using the first 4 non-zero terms of the Taylor series of e to the x centered around x is equal to 1 is equal to e plus e times x minus 1 plus e times x minus 1 squared divided by 2 plus e times x minus 1 cubed divided by 3 factorial. Most of the time, you can keep 3 factorial instead of converting it into 3 times 2 times 1 equals 6, so it looks nicer, but you have to remember that's factorial and not just plain. However, if it asks for the Taylor series of sine or cosine, then the non-zero part matters. Let's say we want to write the Taylor series of sine around x equals 0 after the first 4 non-zero terms. Let's get to plug into the nice and friendly Taylor series formula I showed you earlier. Since we're basing everything off x equals 0, c is equal to 0, since we're centered around 0. If f of x is equal to sine of x, then f of c is equal to sine of c, which is equal to sine of 0, which is equal to 0. Well, that's certainly not non-zero terms, so we have to move on to f prime of c times x minus c. F prime of x is equal to the derivative of sine of x, which is equal to cosine of x. F prime of c is equal to cosine of c, which is equal to cosine of 0, is equal to 1. F prime of c times x minus c is equal to 1 times x minus 0, which is equal to x. F double prime of c is equal to negative sine of 0, which is equal to 0, so that's another term we skip. F triple prime of c is equal to negative cosine of c, which is equal to negative 1, so that's fair game. X minus 0 cubed is equal to x cubed, and we can keep 3 factorial for now. The second non-zero term is -1 times x cubed divided by 3 factorial, which is equal to negative x cubed divided by 3 factorial. The other two non-zero terms are x to the fifth divided by 5 factorial and negative x to the seventh power divided by 7 factorial. You can see the pattern here where the next term is the opposite sign and the power and factorial increase by 2 each time. A Taylor series centered around x equals 0 has a special name, maclaurin series. Like how McDonald's food has 0 health benefits, a maclaurin series is a Taylor series centered around x equals 0. We found the first 4 terms of the maclaurin series of sine of x. There are 4 of these maclaurin series that you should remember. We just found out how to find the maclaurin series of sine of x. Start at x, then alternate between subtracting and adding the next term, while you add 2 to both the factorial on bottom and the exponent up top. The maclaurin of cosine of x is similar to sine of x, but starts at 1, and then, like before, continues alternating while adding 2 to both the exponential and the factorial. First term is actually -1 to the 0th power times x to the 0th divided by 0 factorial, which equals 1. To help remember the difference, remember that sine is shifty, so it has all the odd powers in factorials. Cosine is cool, which means that's even, has all the even powers in factorials, including 0. Both have their positives and negatives, but they start out positive to begin their day, meaning to begin their series. The third of these is e to the x. We did a Taylor series question in e to the x already, and if you remember how that one went, you could see a pattern going on with the powers of factorials. E to the x has the exponent and the factorial start at 0, and it keeps on adding 1 to both forever. It's also always positive. In series notation, it's the infinite sum starting from n equals 0 of x to the n divided by n factorial. Remember, e to the x has the exponent and the factorial start at 0, then go up by 1 every term. The last one is a little different. This is 1 divided by 1 plus x. This one doesn't have any factorial, it's just alternating between adding and subtracting powers and adding 1 to the power each term. Now the other 3 maclaurin series were perfect estimates at any value of x, but 1 divided by 1 plus x is only good for -1 is less than x, which is less than 1. This is because, if you notice, this is secretly an alternating geometric series. As a quick reminder, geometric series look like this, and these only converge if absolute value of r is less than 1. Since to converge, the term has to eventually equal 0 at the limit. Since we're always starting at n equals 0 for Taylor and Maclaurin series, k is equal to 0. So that removes the r to the k part. Thus, if a is equal to 1 and we substitute r for x, we can see that the infinite sum starting at n equals 0 of x to the n is equal to 1 divided by 1 minus x. If we plugged in negative x instead to get 1 divided by 1 plus x, which is 1 divided by 1 minus negative x, and then the double negative makes x positive, then we'd have the infinite sum starting at n equals 0 of negative x to the n is equal to 1 divided by 1 plus x, which we can expand out to -1 to the n times x to the n. To remember that neat little interaction between the two, remember that 1 divided by 1 plus x is head over heels for its beloved x to the n. It's always alternating between hot and cold or positive and negative, instead of its always positive partner. So, just as a final mimetic recap before I run out of time and Memorial Day to finish this video, sine of x is shifty, so it looks always odd on top and bottom. Cosine of x is cool, so it looks always even on top and bottom, and both of them alternate. 1 divided by 1 plus x is head over heels for x to the n, but always alternates instead of being always positive. And e to the x has the exponent and the factorial increased by 1 each term, and is always positive. I am now officially out of time to make this video. I am 93 slides in, and honestly, I'm a little surprised I even made it this far. Do your best to snag what points you can out of the FRQs and MCQs. I hope that the creation I have given rise to will help you remember the basics of how Taylors and McLaurins work out. Have a good day, and I wish you all well on your future tests.